So we're ready to start the scientific program. I'm going to call on Jim Cronin, our chair, to introduce our first speaker.
It's my pleasure to be able to participate in this symposium. Just around the corner, we lived in the same apartment building as Lalitha and Chandra. Got to know them very well. I'll make some remarks about that this evening. But I have the great opportunity to introduce a person I'm very, very admire, which is Professor Freeman Dyson. I always look forward to his essays and his book reviews in the New York Review of Books. I don't always agree with him, particularly about particle physics, but that's another matter. And so with no further ado, let me introduce Professor Freeman Dyson of the Institute for Advanced Study, who is going to speak the subject, Chandra's Role in 20th Century Science. Now, I have a bunch of signs to keep you in time, but I'm not going to use them. I will rely on you.
So that's very unwise, but...
well, then I may use them if
yes,
necessary.
Please do. Anyway, no, I should apologize for reading from a text. That's the only way of being moderately sure of staying within the 3/4 of an hour I'm supposed to take. So in 1946, Subramanian Chandrasekhar gave a talk here in Chicago with the title, The Scientist. He was then 35 years old, less than halfway through his life, less than a third of the way through his career as a scientist, but he was already reflecting deeply on the meaning and purpose of his work. His talk was one of a series of public lectures organized by Robert Hutchins, then the Chancellor of the University. The list of speakers is impressive, including Frank Lloyd Wright, John von Neumann, Arnold Schoenberg, and Marc Chagall. That list proves two things. It shows that Hutchins was an impresario with remarkable powers of persuasion, and he already recognized Chandra as a world-class artist, whose medium happened to be theories of the universe rather than music or paint. I call him Chandra because that's the name his friends used for him when he was alive. Chandra began his talk with a description of two kinds of scientific inquiry. So now I quote from Chandra, "I want to draw your attention to one broad division of the physical sciences which has to be kept in mind, the division into a basic science and a derived science. You'll notice that the division is not between pure science and applied science. I shall not be concerned with applied science, as I don't believe the true values of science are to be found in the applications. I shall be concerned only with pure science, and it is the division of this into basic and derived that I wish to draw to your attention. Broadly speaking, we may say basic science seeks to analyze the ultimate constitution of matter and the basic concepts of space and time. Derived science, on the other hand, is concerned with the rational ordering of the multifarious aspects of natural phenomena in terms of the basic concepts." End quote. So as examples of basic science, Chandra mentions the discovery of the atomic nucleus by Rutherford and the discovery of the neutron by Chadwick. These discoveries were each made by a simple experiment which revealed the existence of a basic building block of the universe. Rutherford discovered the nucleus by shooting alpha particles at a thin gold foil and observing that some of the alpha particles bounced back. Chadwick discovered the neutron by shooting alpha particles at a beryllium target and observing that the resulting radiation collided with other nuclei in the way expected for a massive neutral twin of the proton. As examples of derived science, Chandra mentions the discovery by Edmund Halley in 1705 that the comet bearing his name had appeared periodically in the sky at least 4 times in recorded history, with an elliptical orbit described by Newton's law of gravitation. And as a second example, the discovery by William Herschel in 1803 that the orbits of binary stars are governed by the same law of gravitation operating beyond our solar system. The observations of Halley and Herschel did not reveal new building blocks, but they vastly extended the range of phenomena that the basic science of Newton could explain. Chandra was saying the basic and the derived discoveries are equally essential to the progress of science. He said, a quote again from Chandra, "A very distinguished physicist, apparently feeling sorry for my preoccupation with things astronomical, and with an intent to cheer me up, said I should really have been a physicist." To my mind, this attitude represents a misunderstanding of the real values of science. And the history of science contradicts it. From the time of Newton to the beginning of this century, the whole science of dynamics and its derivative celestial mechanics have consisted entirely in amplification, elaboration, and working out the consequences of the laws of Newton. Halley, Laplace, Lagrange, Hamilton, Jacobi, Poincaré, all of them were content to spend a large part of their scientific efforts doing exactly this in the furtherance of derived science. Indeed, there is a complementary relationship between basic and derived. The basic concepts gain their validity in proportion to the extent of the domain of natural phenomena which can be analyzed in terms of them. Looked at in this way, science is a perpetual becoming, and it is in sharing its progress in common effort that the values of science are achieved. Chandra then went on to describe particular examples of basic and derived science that played the decisive role in his own intellectual development. In the year 1926, when Chandra was 15 years old, but already a physics student at Presidency College in Madras, Fermi and Dirac independently discovered the basic concept of Fermi-Dirac statistics. The basic concept says that when we have a crowd of electrons distributed over a crowd of quantum states, each quantum state can be occupied by at most one electron, and the probability that a state is occupied is given by a simple function of the temperature. This solved one of the most famous unsolved problems of condensed matter physics, explaining why the specific heats of solid materials decrease with temperature, going rapidly to zero as the temperature goes to zero. 2 years later, in 1928, the famous German professor Arnold Sommerfeld, one of the chief architects of quantum mechanics, came for a visit to Presidency College. Chandra was well prepared. Chandra had read and understood Sommerfeld's classic textbook, Atomic Structure and Spectral Lines. He boldly introduced himself to Sommerfeld, and Sommerfeld took the time to tell him about the latest work of Fermi and Dirac. Sommerfeld gave this young student, then 17 years old, the galley proofs of his paper on the electron theory of metals, a paper which was not yet published and gave the decisive confirmation of Fermi-Dirac statistics. Sommerfeld's paper was a masterpiece of derived science, showing how the basic concept of Fermi and Dirac could explain in detail why metals exist and how they behave. This young Indian student was one of the first people in the world to read it. 2 years after his meeting with Sommerfeld at the ripe old age of 19, Chandra sailed on the steamship Lloyd Triestino to enroll as a graduate student at Cambridge University. He was to work in Cambridge with Ralph Fowler, who had used Fermi-Dirac statistics to explain the properties of white dwarf stars. White dwarfs are stars that have exhausted their supplies of nuclear energy by burning hydrogen to make helium and carbon and oxygen. They collapse gravitationally to a density many thousands of times greater than normal matter, and then they slowly cool down by radiating away their residual heat. Fowler achieved another triumph of derived science by calculating the relationship between the density and the mass of a white dwarf star, using the concept of Fermi-Dirac statistics as the basis of the calculation. His calculation agreed well with the scanty observations of white dwarfs that were available at that time. I think the total they knew was 3. With the examples of Sommerfeld and Fowler to encourage him, Chandra was sailing to England with the intention of making his own contribution to derived science. On the ship, Chandra quickly found a way to move forward. The calculations of Sommerfeld and Fowler had assumed that the electrons were non-relativistic, obeying the laws of Newtonian mechanics. This assumption was certainly valid for Sommerfeld. Electrons in metals at normal densities have velocities that are very small compared with the speed of light. But for Fowler, the assumption of Newtonian mechanics was not so safe. Electrons in the central regions of white dwarf stars might well be moving fast enough to make relativistic effects important. So Chandra spent his free time on the ship repeating Fowler's calculation of the behavior of a white dwarf star, with the electrons obeying the laws of Einstein's special relativity instead of the laws of Newton. Fowler had calculated a well-defined relationship between the mass and the density of a white dwarf, so that for any given mass there would be a unique central density. For a given chemical composition of the material, the density would be proportional to the square of the mass. This made sense from an intuitive point of view. The more massive the star, the stronger the force of gravity, and the more tightly the star would be squeezed together. The more massive stars would be smaller and fainter, which explained the fact that no white dwarf stars more massive than the Sun had been seen. But to his amazement, Chandra found that the change from Newton to Einstein made a drastic change in the behavior of white dwarf stars. The change from Newton to Einstein makes the matter in the stars more compressible, so that the density becomes greater for a star of given mass. The density does not merely increase faster as the mass increases, but actually tends to infinity as the mass reaches a finite value, which we now call the Chandrasekhar limit. With relativistic electrons, there is a unique model of a white dwarf star for every mass below the Chandrasekhar limit, and there are no models at all with mass greater than the limit. The limiting mass depends on the chemical composition of the star. For stars which have burned up their hydrogen, the limit is about 1.5 times the mass of our Sun. Chandra finished his calculation before he reached England and never had any doubt that the conclusion was correct. But when he arrived in England and showed his results to Fowler, Fowler was friendly but unconvinced. Fowler was not willing to sponsor Chandra's paper for publication by the Royal Society in Britain. Chandra did not wait for Fowler's approval, but sent a brief version of the paper to the Astrophysical Journal in America. The Astrophysical Journal sent it to Carl Eckardt, a famous geophysicist who did not know much about astronomy, as the referee. Eckardt accepted it, and it was published a year later. Chandra had a cool head. He had no wish to engage in public polemics with the British dignitaries who failed to understand his argument. He published his work quietly in a reputable astronomical journal, and then waited patiently for the next generation of astronomers to recognize its importance. Meanwhile, he remained on friendly terms with Fowler and the rest of the British academic establishment, and he would find other problems of derived science which his mastery of mathematics and physics would allow him to solve. So that's the end of section 1. Section 2, the decline and fall of Aristotle. There were good reasons for the astronomers to react with skepticism to Chandra's statements in 1930. The implications of his discovery of the limiting mass were totally baffling. All over the sky we see an abundance of stars cheerfully shining with masses greater than the limit. Chandra's calculation says that when these stars burn up their nuclear fuel, there exists no equilibrium states into which they can cool down. What then can a massive star do when it runs out of fuel? Chandra had no answer to that question, and neither did anyone else when he raised it in 1930. The answer to Chandra's question was discovered in 1939 by Robert Oppenheimer and his student Hartland Snyder. Oppenheimer and Snyder published their answer in a paper on continued gravitational contraction in the Physical Review. In my opinion, this was Oppenheimer's most important contribution to science. Like Chandra's contribution 9 years earlier, it was a masterpiece of derived science, taking the basic equations of Einstein and showing that they give rise to startling and unexpected consequences in the real world of astronomy. The difference between Chandra and Oppenheimer was that Chandra started with Einstein's 1905 theory of special relativity, while Oppenheimer started with Einstein's 1915 theory of general relativity. Oppenheimer, in 1939, was one of the few physicists who took general relativity seriously. At that time, it was an unfashionable subject of interest mainly to philosophers and mathematicians. Oppenheimer knew how to use it as a working tool to answer questions about real objects in the sky. Oppenheimer and Snyder accepted Chandra's conclusion that there exist no static equilibrium states for a cold star with a mass larger than the Chandra limit. Therefore, the fate of a massive star at the end of its life must be dynamic and not static. They worked out the solution to the equations of general relativity for a massive star dynamically collapsing under its own weight. They discovered that there does exist a dynamic solution of the equations with the star in a state of permanent free fall. Permanent free fall means that the star continues forever to fall inward toward its center, but never reaches the bottom. General relativity allows this paradoxical behavior because the time measured by an observer outside the star is running faster than the time measured by an observer inside. The time measured on the outside goes all the way from now to the end of the universe, while the time measured on the inside runs only for a few days. After the gravitational collapse, the inside observer will see the star still falling freely at high speed, while the outside observer sees it quickly slowing down. That state of permanent free fall is, so far as we know, the actual state of every massive object that runs out of fuel. We now know that such objects are abundant in the universe. We call them black holes. So with 70 years of hindsight, we can see that Chandra's discovery of the limiting mass and the Oppenheimer-Snyder discovery of permanent free fall were major turning points in the history of science. These discoveries marked the final end of the Aristotelian vision that had dominated astronomy for 2,000 years. The vision of the heavens as a realm of peace and perfection contrasted with the earth as the realm of strife and change. Chandra and Oppenheimer demonstrated that Aristotle was wrong. In a universe dominated by gravitation, no peaceful equilibrium is possible. During the 1930s, between the theoretical insights of Chandra and Oppenheimer, Fritz Zwicky, with his systematic observations of supernova explosions, was confirming the fact that we live in a violent universe. During the same decade, Zwicky discovered the dark matter whose gravitation dominates the dynamics of large-scale structures. After 1939, astronomers slowly and reluctantly abandoned the Aristotelian universe as more evidence accumulated of violent events in the heavens. Radio and X-ray telescopes revealed a universe full of shock waves and high-temperature plasmas with outbursts of extreme violence associated in one way or another with black holes. Every child learning science in school and every viewer watching popular scientific documentary programs on television now knows that we live in a violent universe. The violent universe has become a part of the prevailing culture. We know that an asteroid collided with the Earth 65 million years ago and caused the extinction of the dinosaurs. We know that every atom of silver or gold was cooked in the debris of a massive star at the end of its life and thrown out into space by a supernova explosion. We know that life survived on our planet for billions of years because we are living in a quiet corner of a quiet galaxy, far removed from the explosive violence that we see all around us in more turbulent parts of the universe. Astronomy has changed its character totally during the last 100 years. 100 years ago, the main theme of astronomy was to explore a quiet and unchanging landscape. Today, the main theme is to observe and explain the celestial fireworks that are the evidence of violent change. This radical transformation in our picture of the universe began on the good ship Lloyd Triestino when the 19-year-old Chandra discovered that there can be no stable equilibrium for a massive star. It always seems strange to me that the work of those three pioneers of the violent universe, Chandra, Oppenheimer, and Zwicky, received so little recognition and acclaim at the time when they were doing it. The neglect of their discoveries was due in part to the fact that all three of them came from outside the astronomical profession. The professional astronomers of the 1930s were conservative in their view of the universe and also in their social organization. They saw the universe as a peaceful domain which they knew how to explore with the standard tools of their trade. They were not inclined to take seriously the claims of outsiders with new ideas and new tools. It was easy for the astronomers to ignore the outsiders because the new discoveries did not fit into the accepted ways of thinking, and the discoverers did not fit into the established astronomical community. In addition to those reasons for neglect, which applied to all three of the pioneers, there were special circumstances which existed for each of them separately. In the case of Chandra, the special circumstances were the personalities of Eddington and Milne, who were the leading astronomers in England when Chandra came. Eddington and Milne both had private theories of stellar structure in which they firmly believed, and both were inconsistent with Chandra's calculation of a limiting mass. Both of them promptly decided that Chandra's calculation was wrong, and they never accepted the physical facts on which the calculation is based. In the case of Zwicky, an even worse situation existed at the California Institute of Technology, where the astronomy department was dominated by Hubble and Baade, and Zwicky belonged to the physics department and had no official credentials as an astronomer. Hubble and Baade believed that Zwicky was crazy, and he believed that they were stupid. Both beliefs had some basis in fact. Zwicky had beaten the astronomers at their own game of observing the heavens, using a wide-field Schmidt camera that could cover the sky 100 times faster than other telescopes existing at that time. Zwicky had then made an enemy of Baade by accusing him of being a Nazi. As a result, Zwicky's discoveries were largely ignored for the next 20 years. In the case of Oppenheimer, the neglect of his greatest contribution to science was mostly due to an accident of history. His paper with Snyder establishing in 4 pages the physical reality of black holes, was published in the Physical Review on September 1st, 1939, the same day on which Hitler sent his armies into Poland and began the Second World War. In addition to the distraction created by Hitler, the same issue of the Physical Review contained the monumental paper by Bohr and Wheeler on the theory of nuclear fission, spelling out for all who could read between the lines the possibilities of nuclear power and nuclear weapons. So it's not surprising that the understanding of black holes was pushed aside by the more urgent excitements of war and nuclear energy. So it happened that each of the 3 revolutionary pioneers, after a brief period of revolutionary discovery and a brief publication, lost interest in fighting for the revolution. Chandra enjoyed 7 peaceful years in Europe, mostly working on the theory of normal stars without revolutionary implications, before he moved to America. Zwicky, after finishing the sky survey which revealed the existence of dark matter and several types of supernovae, turned his attention to military problems as World War II was beginning, and he became an expert in rocketry. Oppenheimer, after discovering the most important astronomical consequence of general relativity, turned his attention to mundane nuclear explosions and became the director of Los Alamos. When I tried in later years to start conversations with Oppenheimer about the importance of black holes in the evolution of the universe, he was as unwilling to talk about black holes as he was to talk about his work at Los Alamos. Oppenheimer suffered from an extreme form of the prejudice which is prevalent among theoretical physicists, overvaluing pure science and undervaluing derived science. For Oppenheimer, the only activity worthy of the talents of a first-rate scientist was the search for new laws of nature. The study of the consequences of old laws was an activity for graduate students or for third-rate hacks. He had no desire to return in later years to the study of black holes, the area in which he had made his most important contribution to science and might have continued to make important contributions in the 1950s. In the 1950s, black holes were an unfashionable subject, and Oppenheimer preferred to follow the latest fashion. Oppenheimer and Zwicky did not, like Chandra, live long enough to see their revolutionary ideas adopted by a younger generation and absorbed into the mainstream of astronomy. Chandra had to wait 53 years after his discovery before his work was recognized by the Nobel Prize Committee in Stockholm. In his speech at the banquet in Stockholm, he quoted a passage from Virginia Woolf's novel The Waves, which he also used as the epigraph at the beginning of his book on ellipsoidal figures of equilibrium. So here's the quote from Virginia Woolf. "There is a square, there is an oblong. The players take the square and place it upon the oblong. They place it very accurately. They make a perfect dwelling place. Very little is left outside. The structure is now visible. What was inchoate is here stated. We are not so various or so mean. We have made oblongs and stood them upon squares. This is our triumph. This is our consolation." Virginia Woolf expresses in simple words Chandra's unique quality as a scientist. He chooses problems to study without concern for their practical importance. He chooses them for their intrinsic beauty. He devotes to every problem, important or unimportant, the same intensity of creative thought. After each problem is solved, the solution is written down and published with the same meticulous attention to detail. His books are masterpieces of literary style as well as scientific substance. He is, as Robert Hutchins recognized, an artist on the same level as Frank Lloyd Wright and Marc Chagall. So section 3, the polarization of light in the daytime sky. I met Chandra for the first time in the summer of 1950 at the University of Michigan. In those days, the University of Michigan continued the tradition which was established in the 1920s, inviting leading physicists from all over the world to take part in a leisurely summer school, giving lectures and exchanging ideas. Since many of the speakers traveled by ship from Europe, it made sense for them to stay for a month or longer. It was a great opportunity for students like me to listen to the lectures and get to know the famous lecturers. Chandra gave a lecture on the polarization of sunlight in the daytime sky. This was a classical example of derived science, applying to our familiar blue sky the theory that he had worked out in earlier years for the accurate understanding of radiation transport in stellar atmospheres. The atmosphere of a star has much greater optical depth than the atmosphere of the Earth, but even in the Earth's atmosphere, the multiple scattering of sunlight is important. Chandra took delight in calculating the multiple scattering accurately enough to explain the precise measurements of polarization made by observers in the 19th century. Chandra's lecture was a masterpiece of presentation. He took an unimportant episode in the history of science and converted it into a drama. There are in the daytime sky 3 points where the polarization is 0. The 3 points were discovered in turn by 3 famous scientists who gave them their names: the Babinet point, the Brewster point, and the Arago point. Brewster was British and the other 2 were French. Arago was not only a famous astronomer, but a brilliant popularizer of science. The Arago point was the last to be discovered and the most difficult for Chandra to explain. If the calculation is not done precisely right, the Arago point disappears or moves to a completely wrong point in the sky. Chandra's talk filled me with the same kind of joy as the lectures which I'd heard as a student in Cambridge from the pure mathematician Hardy. Chandra had known Hardy well during the years he spent as a student in Cambridge, and he found Hardy a kindred spirit. Chandra and Hardy had similar views about British imperialism and Indian politics, and they had similar tastes in science. Hardy lectured about the summability of divergent series with the same passion that Chandra devoted to the polarization of daylight. The high point of Hardy's story was the construction by Andrei Kolmogorov of a Fourier series that is almost everywhere divergent. The high point of Chandra's story is the construction by George Stokes of a matrix algebra describing precisely the statistics of elliptically polarized light. Both of them reminded me of Wanda Landowska, a great musician who used to play Bach fugues on a harpsichord. The polarization of light in the daytime sky is like a Bach fugue, a work of art with deep resonances in a small space. Another link between Chandra and Hardy was the Indian mathematician Srinivasa Ramanujan. Ramanujan was a mathematical genius who grew up in South India, not far from Chandra's home in Madras, but 23 years earlier. Ramanujan was invited by Hardy to work with him in Cambridge and spent the 5 years from 1914 to 19 in England, becoming a Fellow of Trinity College, Cambridge, and a Fellow of the Royal Society, the first Indian to receive either of these honors. His mathematical collaboration with Hardy was the high point in both of their lives. Chandra was 9 years old when Ramanujan returned in triumph to India, and the stories that Chandra heard about Ramanujan encouraged Chandra to become a mathematician. Chandra did not know then that Ramanujan was mortally ill with amoebic hepatitis and would die only 1 year later. In 1936, after Chandra and Hardy had become friends, Hardy was publishing a book about Ramanujan and needed a good picture of him for the frontispiece. Hardy said the only available picture showed him in academic cap and gown and made him look ridiculous. Hardy asked Chandra if he could find a better picture the next time he was traveling home to India. Chandra took the trouble to find out where Ramanujan's widow was living in great poverty and in complete obscurity, and he invited her to visit with his family. She still had Ramanujan's passport in her possession, with a much better picture which Hardy used for his book. Just as Hardy always remained proud of having discovered Ramanujan, Chandra remained proud of having discovered Ramanujan's picture. Chandra also made successful efforts to organize an adequate pension for Ramanujan's widow so that she could live the rest of her life independently and be treated with the respect that was her due. Hardy and Chandra shared an intense belief in mathematical beauty as the essential quality of good science. That was what attracted both of them to Ramanujan. Both of them wrote eloquently about beauty and about ugliness. Hardy, in his little book, A Mathematician's Apology, gave the classic definition of usefulness in science. This is now a quote from Hardy. A science is said to be useful if its development tends to accentuate the existing inequalities in the distribution of wealth or more directly promotes the destruction of human life. In Hardy's mind, usefulness was almost synonymous with ugliness. Hardy and Ramanujan published jointly in 1918 a paper, Asymptotic Formulae in Combinatory Analysis, a monument to Ramanujan's genius and Hardy's good taste, describing their most elegant discovery in the theory of numbers. The discovery reveals a deep connection between the most elementary additive properties of ordinary integers and the abstract symmetries of the modular group in the theory of elliptic functions. The paper is written in a literary style worthy of Virginia Woolf. This classic work of Hardy and Ramanujan is another example of derived science, according to Chandra's definition. Hardy and Ramanujan did not discover a new mathematical concept or a new law of nature. What they discovered was a deep connection between old concepts, and the new connection extended the reach of our understanding in many directions. Throughout his long life, Chandra devoted himself to many different areas of science, and he found structures of unexpected mathematical beauty wherever he looked. The polarization of sunlight in the daytime sky was one of the smaller items in his cabinet of natural wonders. He was then 40 years old, halfway through his career. When he was younger, he wrote about natural wonders in the dry professional style customary for articles in scientific journals. Only toward the end of his life, like Hardy, he wrote in a more personal style about the quest for beauty. In 1975, when he was in his 60s, he gave a lecture here in Chicago with the title Shakespeare, Newton, and Beethoven, or Patterns of Creativity, describing his various encounters with beauty in art and science. He took advantage of his status as an honored sage to spread his wisdom over a wide field. At the end of the lecture, he comes back to the unique scientific object which is to him the supreme example of natural beauty. This is now a quote from Chandra. In my entire scientific life, extending over 45 years, the most shattering experience has been the realization that an exact solution of Einstein's equations of general relativity, discovered by the New Zealand mathematician Roy Kerr, provides the absolutely exact representation of untold numbers of massive black holes that populate the universe. This shuddering before the beautiful This incredible fact that a discovery motivated by a search after the beautiful in mathematics should find its exact replica in nature persuades me to say that beauty is that to which the human mind responds at its deepest and most profound. So the final section, ellipsoids and black holes. The pattern of Chandra's life as a scholar was to spend 5 or 10 years on each field of science he wished to study in depth. He'd take a year to master the subject, a few more years to publish a series of journal articles demolishing the problems that he could solve, and then a few more years writing a definitive book, surveying the subject as he left it for his successors. After each book was finished, he left that field alone and looked for the next field to study. This pattern was repeated 8 times and was recorded in the titles of his 8 books. First, An Introduction to the Study of Stellar Structure, 1939, summarizes his work on the internal structure of white dwarfs and other types of stars. Second, Principles of Stellar Dynamics, 1943, describes his highly original work on the statistical theory of stellar motions in clusters and in galaxies. Third, Radiative Transfer, 1950, provides the first accurate theory of radiation transport in stellar atmospheres. This is the theory he applied to the Earth's atmosphere in his Michigan lecture. Fourth, Hydrodynamic and Hydromagnetic Stability provided a foundation for the theory of all kinds of astronomical objects, including stars and accretion disks and galaxies, which may become unstable as a result of differential rotation. Fifth, Ellipsoidal Figures of Equilibrium, 1968, goes back to an old problem to discover all the possible equilibrium configurations of an incompressible liquid mass rotating in its own gravitational field. This problem was studied by the great mathematicians of the 19th century, Jacobi, Dedekind, Dirichlet, and Riemann, who were unable to determine which of the various configurations were stable. In the introduction to his book, Chandra remarks, these questions were to remain unanswered for more than 100 years. The reason for this total neglect must in part be attributed to a spectacular discovery by Poincaré, which channeled all subsequent investigations along directions which appeared rich with possibilities, but the long quest that it entailed turned out in the end to be after a chimera. After the ellipsoidal figures of equilibrium came a gap of 15 years before the next book, number 6, The Mathematical Theory of Black Holes, 1983. These 15 years were the time when Chandra worked hardest and most intensively on the subject closest to his heart, the precise mathematical description of black holes and their interactions with surrounding fields and particles. His book on black holes was his farewell to technical research, as Shakespeare's The Tempest was his farewell to writing plays. After the black hole book was published, Chandra lectured and wrote about non-technical themes, about the works of Shakespeare and Beethoven and Shelley, about the relationship between art and science. A collection of his lectures for the general public was published in book number 7, Truth and Beauty, 1987. Finally, during the years of his retirement, he spent much of his time working his way through the Principia Mathematica of Newton, reconstructing every proposition and every demonstration, translating the geometrical arguments of Newton into the algebraic language familiar to modern scientists. The results of this historical research were published in his last book, number 8, Newton's Principia for the Modern Reader, 1995, shortly before his death. To explain why he wrote that book, he said, "I'm convinced that one's knowledge of the physical sciences is incomplete without a study of the Principia, in the same way that one's knowledge of literature is incomplete without a knowledge of Shakespeare. To summarize, this is my assessment of Chandra's role in 20th century science. I would say he made two transcendent contributions separated by 50 years. At the age of 19, he started a revolution in our understanding of the universe by discovering the mass limit for permanently stable stars. This discovery implied, as an inevitable consequence, that all objects with mass greater than the limit must get rid of their excess mass by one means or another. As a result, the universe at large is no longer the quiet domain imagined by Aristotle, but a much more dynamic realm of violent instabilities and cosmic cataclysms. At the age of 72, Chandra published the book that permanently established the true picture of the final state of massive objects. The true picture is the Kerr solution of the equations of general relativity describing rotating black holes. These are the objects that sit at the centers of galaxies, most of the time quiescent, but from time to time causing the titanic eruptions of energy that we call quasars and gamma ray bursts, visible to our instruments from all over the universe, 9/10 of the way back to the beginning of time. Chandra's work on black holes was the most dramatic example of his commitment to derived science as a tool for understanding nature. Our basic understanding of the nature of space and time rests on two foundations. First, the equations of general relativity discovered by Einstein, and second, the black hole solutions of these equations discovered by Schwarzschild and Kerr and explored in depth by Chandra. To write down the basic equations is certainly a big step toward understanding, but it's not enough. To reach a real understanding of space and time, it's necessary to construct the solutions of the equations and to explore all their unexpected consequences. Chandra never said that he understood more about space and time than Einstein did, but it was true. Thank you.
Thank you, Professor Dyson. Instead of worrying about whether you run over time, you could speak forever as far as I'm concerned. It was absolutely beautiful. And I think Professor Dyson will be happy to answer some questions.
Good.
Yes. Yes. This is Jerry O'Connor. Certainly your account of the white dwarf mass number is accurate. But I reread it one time. I read at one point in 1931 monthly notices paper, and I recently reread it. And the surprising thing is that he actually states that you can make white dwarfs of any mass, and that above a certain mass, the critical mass, they are maximum density and are incompressible. And after that, the mass continues with a constant density sequence of homogeneous objects up to very large masses. So he must have had some doubts, at least in 1931, that you couldn't make things more massive than the Chandrasekhar mass limit. He recognized the discontinuity there, but he assumed that above that point they had a fixed density and you could make them of any mass. He later, of course, changed his mind.
No, thank you for putting me right. Just, no, it's true of almost every big discovery in physics or in other sciences too. The person who discovers it doesn't really understand it. And understanding only comes later. And that's certainly true in this case. Chandra himself took him several years to realize really the implications. Hello, here's Mike Nauenberg.
Let me add to Professor Ostreicher's comment. Recently I've written an extensive historical article in the Journal of Astronomy on the subject of the discovery of the mass limit. First of all, let me point out that Fowler, who did the first work on using not really the statistics but the exclusion principle, because there's no need for statistics to look at zero temperature stars. What really matters is the exclusion principle. The reason why Fowler did his work is because a student of his in Cambridge by the name of Stoner actually pointed out the exclusion principle before Pauli. And originally he got credit for it, but then Pauli came into the picture that Stoner's work was soon forgotten. So the second comment I want to make is that Edmund Stoner was the first one to actually apply the exclusion principle and make use of the relativistic equations to show in an extremely beautiful paper the fact that there was a limiting mass. And he worked the equation of state for all densities, which at the time Chandra didn't have. And he showed the existence of the limit. According to Chandra's account, he only found out about this work of Stoner when he arrived in Cambridge. Chandra began his work with Milne, not with Fowler. Milne was his mentor, and Milne offered to publish Chandra's paper too, but for reasons of Chandra's own, he decided to submit it to the Astrophysical Journal in America rather than to the journal Philosophical Journal in England. The other comment I want to make is that contrary to the general perception that nobody cared or believed in Chandra's work because Eddington and Milne and others disagreed with him, it turns out there's been recent research, historical research again, to show that this is not the case. People like Russell accepted almost immediately the existence of the mass limit. Kuiper, by the way, tried to find observational evidence for it. And it's curious that even to date, there is very little that one can say rigorously about the, although nobody doubts the mass limit, observationally there isn't much evidence for the Chandrasekhar relations because of the difficulty of the composition of white dwarfs. Well, I wanted to make a few comments that although giants like Newton and like Chandra make everything look simple, historically, you know, there are other names. There's Willie Anderson, who happens to be an Estonian in an obscure university there, who also pointed out the mass limit, and Landau are forgotten in this story. Thank you.
So I'm happy to be corrected. It is, because Mike Nauenberg is a real expert on this subject, and I'm not. So it's not surprising he knows more about it than I do.
The gentleman just behind Professor Nauenberg.
I'm Jayant Nadlikar from India. I just want to draw attention to the paper by B. Dutt, which was 1 year before Oppenheimer and Snyder's paper, which you referred to, in which he discusses the same problem of gravitational collapse in general relativity and draws similar conclusions. And this is referred to in Landau and Lifshitz book on classical theory of fields.
Good. So again, I stand corrected, and thank you very much.
The day Chandra received his Nobel Prize for the work that you mentioned, we had a party in the laser building, that's the astrophysical building here, and he told me then, and this is just an amusing side remark, he told me then, you know, the Nobel Prize goes with a large financial part to it, but Fowler had also received a prize. And Fowler's prize was from the Royal Society. And that prize was worth more than his Nobel Prize financially. I said, how come? He said, well, he got a medal from the Royal Society, and this was the only coin or medal ever minted with Edward VIII's likeness on it, and accordingly had an immense numismatic value. And it was worth more than the Nobel Prize. And he said Fowler had donated it to the Royal Society. That's just a side remark.
Yes, there. Right there.
I actually have a question rather than a comment.
Good.
Chandra knew more about space and time than Einstein did. Is there more to be known? And what direction should we be looking to know more about space and time than Chandra did?
So that's a good question. Of course, string theorists, of course, are now looking very hard at whether we have more dimensions than 4. So if that's not space and time, I don't know what is. I mean, it's an active subject of inquiry in many different directions. But the string theory is an obvious one. And then there's quantum gravity, which is another. If gravitational field is quantized, of course, the nature of space and time is drastically changed. I happen to be skeptical about that, but it certainly is an interesting question. Many people thinking about it.
Professor Wally?
After this beautiful lecture, I don't want to enter into big controversies. Michael Neunberg and I, we have big arguments about the historical, who got what credit and what time and so on and so forth. But I just want to correct one statement. Mill did not agree to publish the paper of Chandra. In fact, in 1932 paper, Chandra, because it could not be published, he did not think that it would be published in Royal Society monthly notices. He sent it to Dyson für Physik for publishing the paper. And it happened that Milne was there visiting also, and he did not recommend the publication, and he wrote a note to Chandra. If you publish that paper, your reputation will be ruined. So that's where I cannot recommend the publication of the paper. When after he presented 2 papers to Fowler, Fowler accepted his first paper, but the second paper he sent to Milne. Milne was sitting on it. When he did not answer, then Chandra sent paper to astrophysics. And about Landau, of course, he came a bit later, but he did see the inside, but he attributed this to the violation of quantum mechanics in the internal constitution of stars.
So this is a very good example of the general rule that the job of science is to make things simple. The job of historians is to make things complicated.
You spoke about how the work of
Microphone.
You spoke about how the work of Zwicky and Chandra and Oppenheimer was not recognized for 30 years. Do you think this situation has changed in science? Or what can we do to change about in science? Or are there major discoveries made by people in this room now which won't be recognized for 20 or 30 years?
Yeah, well, of course, we can't see them. Maybe they probably are there, but we don't know it. So I can't answer the question. I'm sorry.
There's something we can do to prevent the iconoclasm of. There's something we can do to prevent the iconoclasm of scientists from preventing these discoveries from coming out as soon as possible.
So I don't know. I leave that to the historians. It's too complicated for me.
This one last question. There, gentleman right there.
It's a brief correction. Ranjit Nair from Delhi. Ramanujan was the second Indian to be elected to the Fellowship of the Royal Society. The first was an engineer in around 1873 or thereabouts.
Good. Well, happy to be corrected again.
Well, thank you all. This is great.